Welcome back. So we were in the middle of the proof of the gradient estimate for the scalar curvature, and we had just derived the lemma that says that I can get something extra out of the gradient of the Ricci tensor compared to the gradient of the scalar curvature. There's this extra term on the right hand side, and this I want to use in this equation, which is also still on the board, for the gradient of the Ricci tensor in order to kill a bad term. Now we have to combine things. And okay, now in this step we go for the gradient estimate and compute the evolution equation of the following term, which scales the same way as the trace-free Ricci tensor squared. So we compute that this is equal to or less or equal to what we just done before in the evolution of the gradient of the scalar curvature. So we have Laplacian of the gradient of the scalar curvature minus 2 times the Hessian of the scalar curvature squared. And then we had some term depending just on n times r times the gradient of the Ricci tensor squared. And then we had from the denominator minus gradient r squared on r squared times the Laplacian of r plus 2 times the Ricci curvature squared. And now, of course, we want this to look like the Laplacian of this quantity, so let's just compute what is the Laplacian of this quantity, and then just do the quotient rule. You get gradient r squared over r minus gradient r squared over r squared dir, and this is equal to Laplacian gradient r squared minus divided by r minus, and then you get twice the same term, minus 2 times gradient r squared gradient ir on r squared, and then from here you get the term with the Laplacian, and finally from the denominator plus 2 gradient r squared over r cubed times gradient r squared gives us a gradient r to the 4 here. So now with this side computation, we immediately see this term here, and we recognize this Laplacian term there. So we can write ddt of this gradient r squared over r as less than the Laplacian of this quantity. And then, now, if you stare at this, we get a good term from here, gradient the Hessian squared, and we get a good term from here because this goes to the other side, gradient r to the 4. On the other hand, we have this bad term here, this cross term, which is like 4 times the Hessian of r times gradient ir times gradient jr. So it turns out that the 2 good terms and this 1 bad term combine to a perfect square to give you minus 2 on r cubed times r times the Hessian minus gradient ir gradient jr squared. So this gets rid of all these gradient terms, And actually, this gradient term here has the right sign. I just throw it away because it's not good enough to really help us. It's just the gradient of the scalar curvature squared, but our bad term involves the gradient of Ricci squared. So we have to keep the bad term, Cn times gradient Ricci squared. And that's it. These are the terms we get. And really the enemy is just this one term. But this is exactly the term that we get from the evolution of the traceless Ricci. So now we combine those two things. So we take so ddt of gradient r squared over r plus a lot of traceless Ricci squared is less than the Laplacian of the same thing. And then I throw away this term here. So I have the bad term Cn times gradient Ricci squared. But then from here we get a good term. And this good term was 2 times delta n times gradient Ricci squared, coming from our lemma, and I multiply this with capital N. That's the good term. And on the other hand, from the right, we had another term which was like C1 times R to the 3 minus delta that came from the evolution equation here, and where we used the, remember the assumption of the main theorem, which makes this a slightly better term than you would expect in view of scale. Now it's clear what you do. You choose n times delta n to be bigger than the C of n. So choose n times delta n to be bigger than Cn, and then you can estimate this by the Laplacian of this thing minus, and the way I did it, I even have something left over, I have a good term left over, but I have this term here, and this of course also gets a factor n. Okay. So now I just have this lower order term, and this lower order term means I've tried to kill by just subtracting a tiny little bit of r squared in this term. So the idea is now to set f to be gradient r squared over r plus n times traceless Ricci squared minus some little eta times r squared. And use the evolution equation for r. Then we see that ddt of r squared is equal to the Laplacian of r squared minus 2 times gradient r squared plus 4 times r times Ricci squared, because that comes from the evolution equation of the scalar curvature. So now applying this to f, we get that ddt of f is less than the Laplacian of f. And minus Cn over 2 times gradient Ricci squared plus n C1 times r to the 3 minus delta, And then from here, from the eta times r squared, I get a minus 4 times eta. And now Ricci squared is bigger than 1 on n times r squared. So I get 4 eta times 1 on n times r cubed. And now, by Young's identity, oops, and I have one bad term here, plus 2 eta gradient r squared. Yes. Now I can choose eta smaller than Cn over 2, so I can absorb this one here, which is eta Cn over 2. You can absorb this in here, and then this in there with Young's identity, so I get that this is less than Laplacian of f plus some c of eta times plus some c of eta, full stop. And c of eta depends on our quantity c1 and on the delta, of course. Okay, so here we have an evolution equation, parabolic inequality for a scalar function where we just have an absolute term c of eta. Now, a constant here will just give a finite time. On a finite time interval, we'll just give a constant. So we call, since the scalar curvature is bigger than 0, and since the manifold is compact, say the scalar curvature is bigger than some R0, bigger than 0, then we had shown that Tmax, this was in one of the earlier lectures, that if the scalar curvature is positive, because of this evolution equation for the scalar curvature, we get blow-up of the scalar curvature at the latest in finite time. So Tmax is less than some constant depending on n times R0 to the minus 2, which is certainly less than infinity. We've done that earlier by comparison with a ODE. So we now have a finite time interval, but on a finite time interval, this means that f can grow at most linear with the rate c eta. So the sup of f on the manifold at up to time t can be at most the sup of f on the initial manifold plus c of eta times t max. And this implies that our f, where is f? F is still on the board. It means that gradient, in particular, it means that gradient of r squared is less than eta times r cubed plus c of eta times r times t max. And now we can absorb this in here, and this is less than 2 eta times gradient r times r to the 3 plus some c tilde of theta. And then completes the gradient estimate. A remark I should make is, if you work a little bit harder, and this may be a good exercise, you can actually show that gradient r squared is less than some constant times r to the 3 over 2 minus sigma, where sigma is still positive, but maybe smaller than the delta that you had from the previous argument. So this breaks the scaling in an even more obvious way, but this is enough for what we want to do. that we have the gradient estimate, we can actually compare the curvature at different points of the manifold. So the hope is to show that if we approach T max, where we know the curvature has to blow up, that then it will have to blow up everywhere, and then our pinching estimate will tell us that it everywhere looks like a round sphere. So now the next step is a proposition where we show that the as t approaches T max, we get first of all that R max tends to infinity, and the ratio of R min, minimum of the scalar curvature divided by the maximum of the scalar curvature, approaches 1 as t approaches T max. As a proof, we know that as t approaches T max, we know that the maximum of Riemann on Mn t at time t is unbounded. That was our theorem characterizing singular times. If we come to the finite, and this has to be finite because of this lower bound on the scalar curvature, if we come to the end of the time interval of smooth existence, the curvature has to become unbounded. Now, by assumption, we get that the Riemann tensor, the whole Riemann tensor, is bounded by a constant times the scalar curvature squared. In fact, the trace-free parts, Weil tensor and traceless Ricci, are by assumption bounded by even a smaller power of R, but certainly it's bounded by the scalar curvature. So this must mean that the scalar curvature is unbounded. So there exists a sequence theta I tending to T max such that the maximum of the scalar curvature at time theta I tends to infinity. So we can make the maximum of the scalar curvature as large as we want. But that means that in our gradient estimate, we can make the constant as small to the first term compared to the first term as we want. So this means in particular for any positive eta, I can choose theta I so close to T max that the gradient of the scalar curvature is less than eta squared times R max to the 3/2 on Mn cross time Mn, let me just write Mn at time theta I. Why? Because I could make it less than, say, 1/2 eta squared R max to the 3/2 times plus C eta, but the C eta can be absorbed into this term times eta squared if since R max tends to infinity. So given eta, I can achieve this on this. So now take a point because of compactness, take a point P naught at time theta I, where, or pi at theta I, where I get that the maximum is attained. So the scalar curvature at pi theta I is the maximum at that time. And then let's see how quickly it can fall off. So let's take any geodesic. Gamma starting at pi. Then along gamma, we get that the scalar curvature at some time s along the geodesic must be bigger than at the beginning, max, minus, well, along geodesic, the gradient of the scalar curvature, ds. Now, for the gradient of the scalar curvature, we put in our estimate, so this is bigger than R max, minus a constant times R max to the 3 on 2 times eta squared. That's the estimate I get from here, times the length of the curve. Now, if I choose the curve no longer than, consider only curves with length of gamma less than, say, eta to the minus 1 times R max to the minus 1/2. Notice that this is the right scale for a length. And then along, and for good measure, throw in a 1 over C1. And then, where's the C1 coming from actually? There's no C1. Just use this estimate, and then we get that this is bigger than R max times 1 minus eta along gamma. Okay? So as long as the curve is no longer than this number, and compared to the scale, it's pretty long because of the eta to the minus 1, the scalar curvature doesn't drop off much. Now, I'm going to use now the pinching estimate to show that along this curve, the Ricci tensor will have to be positive because we are in a regime where the curvature is big, and everything is dominated by the scalar curvature, which we have just estimated from below, and then Meyer's theorem will tell us that these geodesics here are going to reach the whole manifold. Okay, so now notice that the trace-free Ricci which is scalar curvature, second, which is equal to the Ricci tensor minus 1 over n times the scalar curvature times Gij, that this is less than some constant depending on n times the norm of v. But v was estimated by C1 or C0, I think I called it, to the 1/2 times r to the 1 minus delta over 2. So this means that so along, which means that the trace-free Ricci divided by r is less than Cn times C1 to the 1/2 times r to the minus delta. But along our curve, we know r is bigger than most, almost a max. So this is bigger than Cn divided by 1 minus eta times r max to the delta times C1 to the 1/2, which goes along gamma. And this we can make, sorry, not larger, less or equal. So this one we can make arbitrarily small, say less than 1 over 10n. Which means that the Ricci tensor has to be very close to 1 over n times r times Gij. So this means in particular that the Ricci tensor will be bigger than, say, 1 over 2n times the scalar curvature times Gij, and the scalar curvature is bigger than 1 over 2n times 1 minus eta times the maximum of the curvature times Gij along gamma. So we have a lower bound on the Ricci tensor in terms of this fixed number, now a completely fixed number at this time, theta I, and then Meyer's theorem applies. So Meyer's theorem says that if you have a geodesic, if along a geodesic you have that the Ricci curvature is bigger than n minus 1 times some constant kappa squared times Gij, you have exactly such an inequality, then the geodesic must have conjugate points, then there must be conjugate points if the length of the geodesic is bigger than this number to the minus 1 times pi. And of course this is sharp on the sphere. If the curvature is that big, then as you go from north pole to the south pole, you'll reach a conjugate point. It's exactly the limiting case. But this means that our geodesic, so our gamma, has a conjugate point if the length of gamma is bigger than, and here's the constant now, so we have to take r max to the minus 1/2 times some constant depending just on n. But our geodesics that we allow it's still on this board over here, the geodesics that we allow are much longer. We can now choose the eta so small that we definitely reach that length. So all our geodesics are allowed to be that long. So our geodesics are sufficiently long to all have conjugate points. If we choose eta, if eta is small. But this means all our geodesics have conjugate points. If you start from a point, all the geodesics have conjugate points, it means that none of them is minimizing anymore beyond a certain point. So this means we must reach all the points on the manifold, because between 2 points on the manifold we can always find minimizing geodesic which does not have any conjugate points in between. So our geodesic must reach the whole manifold. So these gammas cover all of our manifold. But then our estimate from below is true also at the minimum of the scalar curvature. So the minimum of the scalar curvature at theta I is bigger than 1 minus eta times the maximum of the curvature. And this means that the quotient R min over R max is bigger than 1 minus eta, which of course tends to 1 as the theta i's tends to equals. Okay, so this proves the thing, or the proposition. Okay, right, so now we have reached the stage where we know that the curvature blows up everywhere on the manifold, and this means in particular as a corollary that the trace-free parts after rescaling tend to 0. Now we just have to make this rescaling precise and show that we indeed get a smooth limit of constant curvature. And this rescaling procedure we will do in the next lecture. Thank you.